Okay, we're now going to use these formulas. On 5a and b, these are both arc length ones, so we're using the first formula. So it's very fast formula. It's just the radius, which would be 9, times the angle in radians, which it is in radians on this, 5 pi over 6. And now we're not going to actually use our calculator here. We're going to leave these in terms of pi, which is what we'll be doing pretty much throughout this course. So I would just reduce down, and we get 15 pi over 2, and that is the length. And I'm going to put U for units. That's just so I remember that that's not a radian angle. That's the actual length of that arc. For letter B, there's a couple things that could mess us up on letter B. The first one is we're given the angle that's not the angle we want. So we're given 140, but we want this angle. So a full circle is 360. So 360 minus 140 would give me 220 degrees. Oops. Try that again. 220 degrees. There we go. But then the second thing is we don't want degrees. We want radians. So we need to convert 220 degrees to radians. Back to what we talked about at the top. We're going to multiply that by pi over 180. Now, again, I'm going to leave this in terms of pi, so I'm not actually going to multiply it in a calculator. I'm basically just going to reduce the 220 and the 180. So 10 goes into both of them, so the zeros are gone. Then 2 goes into 18 9 times, 2 goes into 22 11 times. So that angle measure of 220 is actually an angle measure of 11 pi over 9 radians. Now I can apply my formula. The formula is simply the radius, 5, times the angle, 11 pi over 9. Nothing can reduce, so my arc length is 55 pi over 9. And again, that's just in units, whatever the units are of measure there. For the next one, now we have a backwards problem. So we have a central angle of theta. I have some circle, and this angle might be, oops, this angle might be way too small. I don't know. I'm not worried about it, but I'm going to draw a central angle of theta. The circle has a radius of 9. 9. Really badly drawn 9. Now this time it's telling me the arc length. So it's telling me the length of the arc is 14. I want the measure of the angle. So I'm still going to use the same formula that I've been using. S equals r theta. But this time I'm going to be solving for theta. So S in this case is 14. R was 9. And I'm solving for theta. So I just need to divide over 9. And I get that theta is 14 over 9. Now, that sounds weird because every time we've mentioned an angle that's in radians, we've had pi in there. It doesn't have to be, though. This is still a radian measure. Pi is just a convenient number for radians, but it's not that every angle has to have pi in it if it's in radians. On number 7, now we're going to find the area, so we're going to use that other formula. Area is r squared theta over 2. But again, I'm in degrees. I need to be in radians, so off to the side, I've got to convert. Oops. 80 degrees times pi over 180. Again, if I reduce this, it'll come down to 4 pi over 9. So my angle in radians is 4 pi over 9. So now I can throw everything into my formula. The radius, it says, is 8. So 8 squared times 4 pi over 9. And then all divided by 2. You can piece this together however you want. Since it's all multiplication and division, well, after you square the 8, so that'd be 64. And again, you can go about this in whatever order you want. Maybe you want to divide the 64 by the 2 first. You get the 32. And then 32 times 4 will give you 128 pi over 9. And again, on that, that's the area. So I'm going to say units squared. The last problem is actually a really interesting one. And it technically is an area of a sector problem, but I'm going to show you that we don't actually need the formula for the area of a sector for this one. So 3 circles that have radii 1, 2, and 3 feet are externally tangent. Basically, they bump against each other like we could see here. So this smaller circle must be 1 and 1 for its radius. The middle sized circle has a radius of 2. And the longest circle has a radius of 3. Now, here's the issue. We definitely need to know this angle here. Looking at it, it definitely looks like it's 90 degrees, which is pi over 2 radians. But I need to know that for sure. I can't just eyeball it and say, I think it's 90. Here's how I can actually guarantee that it is 90, though. And this is going to use a property from geometry that you may not remember. But if I draw another radius on this big circle, that's also a length of 3, and then another radius on the medium circle, that's another length of 2. Now if I focus on that triangle, well, this side of the triangle is 4. This side of the triangle is 3 total. This side of the triangle is 5. This is a 3, 4, 5 triangle, and if you remember way back from geometry, that is definitely a right triangle. So indeed, this angle here is 90, or pi over 2 in radians. So the fastest way to figure out the area of that shaded piece is to take the area of, the area of that small circle. So just focusing on the small circle now, the area would be pi r squared, but only 90 degrees is filled in, which means only 1/4 of it is. So I'm going to divide it by 4. So that means I have r is 1, so 1 squared is 1 times pi over 4, or pi over 4. And that is the area of that shaded part. You won't see anything like that on the test, but it's an interesting problem, and it also brings back some old geometry stuff.